Imagine a man standing in a dense forest in the early 1800s, holding a long wooden rod while looking through a small telescope. He is miles from any city and surrounded by nothing but mud and mosquitoes, but he is obsessed with a single inch of elevation. If his measurement is off by even a tiny fraction, the massive project behind him will fail, and millions of dollars will wash away in the next rainstorm. This man is a surveyor, and he is the unsung hero of a revolution that changed how humans interact with the planet. We are looking at the era when the world stopped fighting against the landscape and started re-engineering it with surgical precision. Last time, we explored how these artificial waterways finally broke the back of the high costs that kept people isolated and poor. We saw how a single horse could suddenly pull 50 times more weight once it was moving a boat on water instead of a wagon through the mud. But knowing that a canal is a good idea is very different from actually carving one across a continent. It required a shift in thinking from brute force to extreme accuracy, and that shift began with the mastery of a single measurement. Before this period of civil engineering excellence, the world was a collection of local pockets. If you lived 30 miles from a river or a coast, you were effectively cut off from the global economy. Moving heavy goods like coal or grain over land was so expensive that it usually wasn't worth the effort. Roads were often just cleared paths that turned into impassable bogs the moment the weather turned. The problem wasn't a lack of effort, but a lack of a system. People had built small ditches and local canals for centuries, but they were limited by the terrain. If you hit a hill, you stopped. If you hit a valley, you were stuck. The landscape dictated what was possible, and for most of history, the landscape said no. The turning point came when builders realized that they didn't need to find a flat path, they needed to create one. This required a level of mathematical precision that had previously been reserved for astronomers and watchmakers. The breakthrough was the application of the spirit level and the transit on a massive scale. Engineers began to look at the Earth not as a series of obstacles, but as a puzzle to be solved through the measurement of elevation. They developed the concept of a datum line, which is a fixed reference point used to measure the height of every other point on the project. By sticking to this invisible line, they could ensure that water would flow exactly where they wanted it to go, at exactly the speed they required. Think about the sheer audacity of this task in the 1820s. You are trying to build a perfectly level highway of water through hundreds of miles of wilderness. You have to cut through solid rock and build massive embankments over swamps. In places like upstate New York during the construction of the Erie Canal, the engineers had to figure out how to lift boats hundreds of feet into the air to cross a mountain range. They did this through a series of locks, which are essentially water elevators. But a lock only works if the masonry is perfect and the water levels are calculated to the inch. If one lock is slightly out of alignment, the entire system grinds to a halt. This focus on precision triggered a massive leap in logistics and organizational technology. It wasn't just about the dirt and the stone, it was about managing thousands of men and millions of tons of material. This was the birth of the modern construction project. Before this, most big builds were handled by the military or by local landowners using whatever labor they could find. Now you had a new class of professional civil engineers. They had to invent tools as they went along, like specialized plows to cut through thick roots and giant cranes to move massive stones. They had to create supply chains for waterproof cement, which was a high-tech material at the time, that allowed them to build structures that would stay strong even while submerged for decades. The logistics of keeping these projects moving were staggering. Imagine trying to feed and house 5,000 laborers in a swamp before the invention of refrigerated trucks or modern medicine. These canal camps became temporary cities, and the managers had to figure out how to provide thousands of pounds of beef and flour every day. They had to manage payroll across hundreds of miles and deal with the constant threat of disease. This pressure created a new kind of management style that favored efficiency and standardization. They realized that if every lock was built to the same dimensions, then every boat could be built to the same size. This standardization is what truly unlocked the power of the canal. As these systems spread, they created a ripple effect that touched every part of life. Once the engineers proved they could move water and boats through the mountains, the economics of the world changed. Suddenly, it was cheaper to ship a ton of grain from a farm in the middle of the continent to a city on the coast than it was to move it 10 miles by wagon. This meant that farmers were no longer just growing food for their neighbors. They were players in a global market. Small villages that happened to be near a canal lock exploded into major industrial hubs. The cities that sat at the ends of these canals became the most powerful financial centers on Earth because they were the gates through which all this new wealth had to pass. But it wasn't just about the money. It was about the professionalization of knowledge. The men who learned how to build these canals went on to build the railroads and the bridges of the next generation. They developed a common language of blueprints and specifications that allowed someone in one part of the country to understand exactly how a bridge was being built in another. They proved that the physical world could be mastered through data and measurement. This era taught us that if you can measure something accurately, you can manage it. And if you can manage it, you can change the world. Even today, we are living in the world that these canal builders created. Our modern global logistics networks are just a more advanced version of the systems they pioneered. When you look at a massive container ship today, you are seeing the direct descendant of the wooden canal boats that once crawled across the countryside. The way we track packages and manage international shipping lanes relies on the same principles of standardization and precision that were perfected in the mud of the 1800s. We still use the same concepts of elevation and water management to protect our cities and move our resources. The civil engineering of the canal era provided the blueprint for the modern industrial state. It is easy to look at a quiet canal today and see it as a relic of a slower time. But at the peak of its era, it was the fastest and most advanced technology on the planet. It was the internet of its day, a network that moved information and goods at a pace that had never been seen before. The real legacy of the canal era isn't the water or the stone, but the realization that human ingenuity could overcome the constraints of geography. By mastering the measurement of the Earth, we gained the power to reshape it, to fit our needs. Now that we have seen how massive water highways reshaped the map of the world, we need to look at what happens when those systems move from the open countryside into the heart of the city. In the next episode, we stay within the realm of infrastructure, but zoom in to the hidden world beneath the streets to see how engineers tackled the growing crisis of urban waste. This leap from transport to sanitation would redefine the limits of how large a city could actually grow. Be sure to join us as we explore the invisible engineering